For the first talk of this afternoon session, it's a pleasure to introduce Soheil Feizi from University of Maryland. Take it away.
Thank you so much. Thanks for the invitation. Thanks everyone for being here. So today I'm going to talk about studying failure modes of deep learning and potential ways to fix them. Okay, we have all witnessed recent success of deep learning in many areas, ranging from self-driving cars and vision, to robotics, to natural language processing, games, reinforcement learning, you name it. But the question we are asking in this presentation is, in fact, whether deep learning models in practice are reliable. In order to study this question, first we need to say how we can measure reliability. So I'm going to briefly spend some time to explain the second question, and then we are going to talk about the first. Of course, one standard measure of reliability is accuracy, and there have been a lot of work in the last decade to increase accuracy of models on benchmark datasets like ImageNet by either coming up with better architectures or better training approaches in order to basically improve the accuracy on these benchmarks. But obviously, just accuracy alone is not sufficient, and we need to look into some other aspects of these models, such as distributional robustness. Let me explain that with a simple example. Here, if you take some pre-trained models on ImageNet and you evaluate those models on a slightly different data set of ObjectNet. So basically, this data set has the same labels, but objects may have like different orientations or backgrounds. And if you do that, you see a significant drop in the performance by like 40–45 percentage points, meaning that these models are in fact not very robust to these types of distributional shifts in the data set. So another issue is adversarial robustness of these models. Here we are adding some small but potentially imperceptible noise to the input in order to fool the model and have an incorrect classification. Here, for example, your clean input is Egyptian cat for both model and humans, and we are adding a small noise. For humans, still this image is a cat, but for model, the prediction is a traffic light. So that's why we are saying this example is an adversarial example for the model. And we have observed that even in the presence of very small adversarial perturbation, the performance of these models can drop quite significantly from 80% to basically almost 0%. Obviously, we need to consider other aspects like test time interpretability, training time interpretability, fairness, and basically using such an evaluation simplex, we can evaluate models using a radar chart to have a more complete picture of their performance that we'll see in practice. Over the last years, we have studied different aspects of reliability. In the first part of the talk, I'm going to mainly focus on adversarial robustness, which is the theme of this workshop. And I'm going to present some of our recent results in this domain. In the second part of the talk, I'm going to step back and ask this question. If there is a common reason, a root cause behind many of these reliability issues in deep learning, in a way, if we could identify it, resolve it, and deal with it, we can increase reliability of models across the board. So that's going to be the focus of the second part of the talk. And by the way, feel free to interrupt me if you have any questions. Okay, so let's get started. Adversarial robustness problem. So in the adversarial attack problem, the goal is to create an adversarial example X prime by maximizing a classification loss to mislead the model F. And this X prime should belong to a certain set. We call that set a threat model. Probably the most standard threat models are LP threat models, where the LP distance between X and X prime are bounded within a certain threshold rho. And of course, robustness against LP is very important to understand, but by no means it is sufficient, because there are many non-LP attacks that won't fall into the LP threat models, and they can break the system. They can break our model. These non-LP attacks include like attacks like spatial attacks. You spatially change your objects, or some semantic level attacks. You recolor your image in order to create adversarial examples and many, many other examples. Okay, so we are going to mainly focus in this talk on provable or certifiable defenses. What I mean by that, we say a classifier F is certifiably robust at a particular point X if for all points in a certain radius of that point, let's say with a radius rho, the output of the classifier remains the same. Right here in this example, you have X with a green label, and for all points in a radius rho of the X, the label remains the same. And that's what we are saying rho is the certification level or robustness level. Okay, in the last 5 years, I should say there have been a lot of interesting ideas to come up with such provable and certifiable methods against adversarial perturbations. So first, I'm going to categorize them based on the amount of the network information they used in the defense. Again, the attack is white box. Attack can use any information it wants from the network, but I'm going to classify the defenses based on the amount of the network information they use in the defense. So focusing on LP threat models, in one extreme, we have defenses based on randomized smoothing. So basically, these methods, they only look at input-output relationship without looking into the underlying mechanics of the network. And these methods, because of that, they're very scalable to deep models and high-resolution data sets like ImageNet. In the other extreme, we have methods that basically bound the curvature or Lipschitz values of the network. And because of that, it basically bounds the variations of the output with respect to the input and come up with provable robustness. But these methods are successful on shallow networks, but not yet, they are not scalable to deep and practical models. As I mentioned, non-LP attacks are also important. We can think about provable robustness against non-LP attacks. For example, in sparse attacks, adversary can change few pixels in the image in order to craft an adversarial example. In Wasserstein threat model, you normalize an image to view that as a distribution and then bound the Wasserstein distance in order to basically have a model for spatial variations in the adversarial examples. And in patch threat, basically adversary puts an adversarial patch in order to mislead the model. So you can think about provable defenses against these types of non-LP attacks as well. So in the first part of the talk, I'm going to mainly focus on randomized smoothing because, as I mentioned, randomized smoothing is probably like the most practical, certifiable and provable defense that we can use on deep models and high resolution data sets like ImageNet. Okay, so let me first review the basics of randomized smoothing, starting with this paper by Cohen and co-authors. So a smooth classifier is defined as following. So you, yes,
okay,
yes, of course.
On the introduction, so the idea of the idea of robustness here is related to having better classifiers in the sense that they perform better out of sample, or is it the goal to have classifiers that are robust to malicious attempts to sort of trick them? And are these two things different?
They are different. So in the first part, when we are talking about distributional robustness, which I'll talk a little bit later on during the talk, is that you have some natural variations in your inputs. Right? So these are not malicious changes that you are imposing to your input. For example, you have an image of a chair and you classify it correctly on ImageNet, but you go to another data set and maybe the background is a little bit different or the chair orientation is different. So these are natural changes and we want models to be robust to these types of natural changes. In the adversarial robustness that I'm basically the focus of the first part is that we intentionally impose some perturbations to the input in order to make sure the model output doesn't change. And these inputs can be very small. But these perturbations, they can potentially be a function of the model itself in terms of like attack optimization. They are not like just random noise that we are adding to the input. Does that make sense?
Yes. So just a small follow-up question on the first part. So the idea is say, it's okay. I'll ask later if I don't.
Okay, sounds good. Any other questions? Okay, so in smoothing, so we have a base classifier f. This f can be anything. It can be a neural network. It can be even a linear function. It can be anything. So we add some noise to it as input, and we look at the expectation of this function as the smooth function. That's what we call a smooth classifier f bar. And this epsilon noise, it can have different distributions. For example, in Gaussian smoothing, this epsilon is according to a Gaussian density function. The intuition behind the smoothing is that your base classifier may have some sharp decision boundaries, and it creates some adversarial sensitivity. For example, here, if you have an input x here, with a small perturbation, you can go from the green region to the blue region. But if you do smoothing, you're basically smoothing out some of these sharp decision boundaries, and potentially you increase the intrinsic robustness of your model. So how does the robustness guarantees work here? It is basically not hard to show that a smooth classifier can be shown to be provably Lipschitz. I'm going to show one such example. And when you have provable Lipschitzness, then robustness comes for free, because you have a bound on the variations of the outputs with respect to the input. Okay, so that's basically a very quick overview of smoothing. In our ICML paper, we studied the additive smoothing, some issues of additive smoothing. Why I'm saying it is additive? Because you're just adding noise to the input. Right? So you generate some noise from Gaussian or any other distribution, you're adding to the input. So that's additive smoothing. So we identified some issues in additive smoothing. The first one is the curse of dimensionality. We showed that there is an upper bound on the robustness guarantees that any additive smoothing can achieve. And this bound is something like this, that depends on sigma, which is the standard deviation of the noise, d is the dimension, P1 and P2, they are the probabilities of the top class and the runner-up class. But if you think about this bound, the scaling is not good, because with higher dimensions, especially when P is larger than 2, you have some extra dependence on the dimension, and this bound quickly goes to 0. So, yes.
In my mind, at the beginning, I thought that if this L2 attack, I will get a curse of dimensionality just because the variance is something like sigma root d.
Yes.
Right? But if I put p equals 2 there, I get this.
Fantastic question. Fantastic question. So let me repeat the question and then I'll answer that. So here, basically, this is an upper bound for any LP attack. P doesn't have to be 2, right? So the sigma is an element-wise variance of your noise, right? So the magnitude of the noise is basically sigma square root of d. But this radius is the radius of the perturbation of the image. So you have one scaling of square root of d there.
Okay.
But when p is larger than 2, you have an additional dependence on 1. Does that make sense?
Yeah.
So this is a negative result. Basically, you cannot have any smoothing, additive smoothing that can beat this bound, and this bound is not good.
So just to be clear, what is P1x, what is P2x,
Yes.
and what is the robustness radius?
So P1x is the basically the probability of top class for that particular sample is the top logit, and P2x is the runner-up class. What is the second best class for that particular image?
In the given model?
For a given model, yes.
And RP star, what is it?
This is the upper bound on the robustness radius against LP attack.
Maybe like, but of course, changing X to something else will change F bar. Do you impose some closeness within a bar X and perturb?
Yes, so within this LP attack, let's say you have an LP ball of radius rho star of P. So you cannot have a larger radius than this in order to with the same label within that ball.
Oh, but there are some logics, not label. You just want the top label to stay the same?
Yes, because otherwise, you will have a misclassification.
You don't look at the logic.
Exactly. Yes.
So do you assume, what kind of data distribution do you assume to get your?
This is general. So this is general for any data distribution. And not only that, this is true for any additive distribution for the smoothing. It doesn't have to be Gaussian.
Okay, but maybe to be more specific, what if you had high-dimensional data, like up dimension D, but on a low-dimensional matter field? You still get that dependence on D,
Yes.
or does it improve?
It is the same thing. Okay. The other problem, which is more obvious but can be critical in some application, is that we get probabilistic certificates, not deterministic ones, because you can never compute this expectation exactly. Right? So we always have some bounds, upper and lower bounds. With high probability, we can do the certification. You can say maybe 99% probability is good, but in some application that may not be good because you want like to be able to guarantee with 100% certain. So we ask, is it like because of the additivity nature of smoothing, can we come up with some non-additive smoothing distributions in order to improve the certificates in some of these aspects? And that's basically the focus of our other ICML paper with my student, Alex Levin. So here we introduce a method called non-additive smoothing with splitting noise, in short SSN, that will basically lead to some improve properties of the robustness. So first, let me explain the noise distribution with some example. Suppose you have a pixel value between 0 and 1. Before, I'm just adding a Gaussian noise to this X, right? So that's why I'm saying it is additive. So I want to add do some non-additive smoothing on this. So what I'm going to do is that I'm going to first generate a splitting variable uniformly between 0 and 2 lambda. So that's my splitting variable. And then depending on which interval this xi falls, I'm going to map it to the center of that interval. Basically, I'm adding some quantization noise to X, where the quantization level is drawn uniformly, randomly from an interval between 0 and 2 lambda. Very simple noise that we're adding. Okay, but this simple noise, it has some amazing properties. Some of them actually we didn't intend at the beginning, and then I'm going to explain what properties we get. So first of all, we get robustness for free. If you smooth using this distribution with this non-additive splitting noise, the smooth classifier is guaranteed to be 1/2 lambda Lipschitz with respect to the L1 norm. And therefore, you get provable robustness against L1 attacks. So I'm gonna show a simple proof of this and also show some generalization for other LPs. But probably more important than this result is this following property. The splitting variables do not need to be independent. Therefore, smoothing can be done effectively in one dimension and can be de-randomized. So what do I mean by that? So suppose we have a two-dimensional problem for simplicity. Let's say we have a discrete problem like image pixel values. So you have two splitting variables, S1 and S2, in order to add quantization noise, splitting noise to your pixels. So in order to have a deterministic function as you're smoothing, you need to evaluate the output of the function in each of these realizations of these splitting variables. But this can be very, very expensive, especially in high dimensional problems. If we don't need the splitting variables to be independent, I can pick any joint distribution as long as the marginal distributions are uniform. For example, I can pick this distribution as long as, because the marginals is uniform. And just count the number of points that you get. It is basically the same number of points that you get in one of the rows. So it may not seem like a big deal from 2 dimension to 1 dimension, but think about images in ImageNet with 100,000s of dimensions, and effectively we reduce the smoothing to be done in 1 dimension and also provide deterministic guarantees for us. So where this comes from, right? So that is the main property that we have here. What is the intuition behind SSN? Again, for simplicity, let's focus on a 2-dimensional problem. Suppose you have 2 inputs, X and X prime, and you want to add splitting noise to them. Basically, first you generate splitting variables randomly, S1 and S2 for each of the dimensions, and you map x's to the basically the center of these quadrants that they fall into. Here you don't have any collision. So x and x prime, they are mapped to the different points because they are not in the same quadrant. But with some chance, because we are drawing these splitting variables randomly, with some chance, they may happen to be in the same quadrant. And therefore, they're going to be mapped to the same point. So here you have collision. With some probability, you have collision. Now let's look at the difference between the output of the smooth function at x and x prime. It is very easy to show that this is bounded by the probability that their smooth version do not collide. Because if they collide, you get the same value. If they don't collide and the functions are bounded, the range is between 0 and 1, you get this probability. It is very easy to show that. So what is this probability? The probability that they don't collide, their smooth version, is the same as the probability that at least one of their dimensions don't collide. Right? Because if one of the dimensions don't collide, they don't collide. Okay, so how can I compute this probability? I use union bound. Basically, this probability is the probability that my splitting variable happens to cut the distance, the interval between the ith coordinate of x and x prime. And that probability is nothing but the difference in the ith coordinate, which is delta I, over 2 lambda, because the splitting variable is uniform from 0 to 2 lambda. And what you get here, you get L1 norm of delta, which is the distance between x and x prime over 2 lambda. Immediately, this shows it is Lipschitz in maybe 2 lines. Therefore, you can guarantee against perturbations. But more importantly, did I use anywhere the independence of these splitting variables? No, I didn't, because I use union bound. Therefore, I don't have constraints on the joint distributions of these splitting variables, except the marginal should be uniform. That's easy to satisfy. How does this work in practice? It basically works really well. It is the state of the art in terms of provable robustness, even in the ImageNet scale. The red one is the previous state of the art that use uniform noise. And the blue one is the basically curve that we get. Y-axis is the certified radius. We basically double the certified robustness. But not only that, we also get better clean accuracy compared to the previous state of the art. Basically, we get the best of the 2 worlds. So recently, we have extended this to other LP threat models, especially fractional LP threat models. What we do, we consider a more general threat model with this distance. So what is this distance between x and x tilde? I can apply any concave function to the difference between the ith coordinate of x and x tilde. And this concave function should be from 0 to 1 to 0 to 1. At origin, it should be 0. For example, if this is identity, you get L1. But you can get other fractional LP by just picking this function as in this form. For example, you can think about like P is equal to half or 1/3.
I would expect to choose convex. I mean,
Yes.
the distances are convex functional.
It doesn't work for convex. Right? So that's why we need like fractional, we are basically looking at fractional LP. So it's a long story why it doesn't work for LP. I'm happy to talk about it offline. But basically for the concave ones, we show that you can extend the splitting noise to something called variable gamma smoothing that I'm not going to talk because it is fairly technical. And you can get provable robustness. We are going to present it in AIS test this year. But that's a great question. We think that actually there are some negative results for the convex case. I'm happy to chat about that often. Okay, so let me pause here if there are any questions.
So I mean, I guess there's a trade-off here, and I guess from your theory, one side of the trade-off is clear, but the other is not present, which is I can definitely make something super smooth by just having one cell and
Yes.
pointing all images in the center of the cell. So yeah, I guess I didn't see. Like, I mean, like it's only experimental evidence, I guess, that you do better with this approach. But a priori, presumably, you weren't sure if this is going to work or not. I wonder what was the process.
That's a great question. So as Costas mentioned, there's always a, let me just repeat. So there's always a trade-off between certified or robustness, certified accuracy versus clean accuracy, right? Because if you, smooth in the extreme and map everything to one point, then you have amazing robustness, but not so useful model. Of course, we look at different parameters. Sigma is the parameter that we have. We not only get increased robustness, we also get increased clean accuracy compared to the previous state of the art. And this was a little bit surprising at the beginning, but there is actually a reason behind that. Because previous methods, they add just uniform noise, additive uniform noise to the input. And there is a range of the values that the pixel value doesn't carry any information, because any value could be generated because of the magnitude of the uniform noise. But in our case, because we are adding some structured noise, it is much easier for the network to learn that basically value is probably a value without any information. And because of the model learns faster and has better clean accuracy. But of course, we don't have theory on that. So it is just empirical evaluation and some hypothesis that we have.
So just a quick, so this is on the ImageNet.
Yes.
Yeah. Because I thought the philosophy of the exercise was to make them better out of sample. So the funny chairs that you showed at the beginning.
So this part is about adversarial robustness. Right? So in the second part, I'm going to talk a little bit about distributional robustness.
So I guess from the last comment you made, I guess it was implied that it's not just you train some model and then do your smoothing, but like then you go back, like you train the model anticipating you're going to do smoothing on the model that you trained. Correct?
Yeah, so there are some ways, even in the first Gaussian smoothing, usually, like, first of all, you inject noise during training, otherwise the numbers are not good. Or you can do like some other, ways like doing adversarial training and stuff. So we repeat all of those techniques, but of course there is this hyperparameter, which basically we have lambda here that shows like the magnitude of the noise we are adding. We evaluated for a range of it, and that's why we have like, a trade-off curve between robustness and the clean accuracy. Make sense?
Yeah.
Yes.
Post-process situation. Right now, or no. Okay. Sounds silly, but I see in the metrics a D. Does change something in the argument DSSN? Do you mean something?
It is deterministic
okay.
smoothing with splitting noise.
But just because you follow the non-independent case, you call it like that?
Yeah, because the thing is that like we don't need independence, so I can evaluate all of the possible outputs for my noise, because I effectively do smoothing in one dimension. That's why we have determinism here. So not only another, I have to say, another property compared to the previous state of the art is that we are deterministic. So we say it is with 100% we guarantee robustness. Okay, so for the interest of time, oh God, now I have some tough decisions to make. Okay. All right, so we have basically improved robustness, better clean accuracy. It is time to celebrate. Or is it? Okay, so let's go back to the picture that we started with. Basically, we started with this landscape of provable defenses, but there is a hidden assumption here. And that hidden assumption is basically here, that we assume the defense knows the threat model used by the attack. In 99.9% of adversarial robustness work in the literature, this is the assumption. And this is probably like the most unrealistic assumption that you can think about, because by definition, Adversary is not a nice person. You can ask the adversary, oh, my defense is for L2, like, please don't use like other threat models, right? So practically, we need to understand generalization of robustness. So what happens if the defense doesn't know which threat model attack is going to be based on? So this part, we start with a thought experiment. Maybe there's no issue here. We take a data set like CFAR10. We take an adversarial training approach, which has been covered in the workshop. It's a min-max problem. In the max, you find worst perturbations within a threat model. And in the min part, you train your model for those perturbed samples. And let's say we do L-infinity adversarial training. Robust accuracy against L-infinity, we get, roughly speaking, 50%. There are some works improve this number by a couple of percentage points. 50%, not too bad. We are still working to make it better. But now if you look at robust accuracy against L2, you get 20%. And think about this. This is CFAR. 10% is random. Random guessing, you get 10%. But with all of the, the hypes that we have, for L2, we get basically 20%. And this is not just for this particular defense. So we have observed similar behavior across many, many other defenses. It's a joint work with two of my students, Cassidy Laidlaw and Soheil.
Is it the same rule, the same radius?
Roughly speaking, the same, because the metrics are different. So how to translate one to another, I'll talk about it, but both of them are imperceptible. So basically, what we say here is standard defenses, they have poor generalization to unforeseen adversarial attacks. So the question is, how can we develop a defense with improved generalizability to unforeseen threat models when you don't know the threat model ahead of time? Okay, as I mentioned, this is a joint work with my students. Okay, in order to understand this question, we need to understand the relationship between the threat models. Think about this big box as the set of all unconstrained adversarial examples for an input. And think about this blue set as the set of imperceptible adversarial examples. These are the perturbations that humans can't tell the difference between X and X prime. The issue is that we don't have a good mathematical characterization of this set. Therefore, what we do, we try to fill this up using narrow threat models like LP, spatial threat model, patch threat model. But the issue is that even if you have a model that is robust against union of these threat models, you have many, many adversarial examples that do not fall in the union. Therefore, your model can potentially be very vulnerable against those adversarial examples. So instead of this bottom-up approach, we propose a new view to this problem, a top-down view that we directly approximate this set of imperceptible adversarial examples using a neural network. Basically, we look at all X prime such that the neural perceptual distance between X and X prime is within a certain threshold. We call it neural perceptual threat model. Okay, so what distance we use for the neural perceptual as our neural perceptual distance? We use LPIPS, learn perceptual image patch similarity, but our framework is general. Other distances can also be used. So what is LPIPS? So you take a perceptual network G and you have an input X, and you push your X to this network. And then you look at the normalized activations of different layers as a feature extractor for X. So these are basically perceptual, quote unquote, perceptual features for X. Now, if you have another X tilde, another image, you can do the same thing. You can extract phi of X tilde. And if you look at the L2 distance between phi of X and phi of X tilde, that's basically the LPIPS distance or the neural perceptual distance that we use. If for two images, this is less than a threshold, but when you push these images to your model and you get different labels, we call this X tilde a perceptual adversarial example for your model. But of course, the question here is how you can pick these perceptual networks in order to compute these phi of X's. So you can have different choices. One is you take a pre-trained model like AlexNet, and use that as your perceptual network. Or more interestingly, you can use the same network for perceptual feature extraction and for the classification. And if you do that, basically during adversarial training, your threat model is changing. It is adaptive because your model is changing. Okay, so let's look at the attack problem. In the L2 attack, we solve this optimization. Obviously, we do the first order approximation at the beginning, replacing the objective with its first order approximation. And the constraint is convex. So we can solve this exactly. And the solution is basically follow the gradient and project if you're outside of the ball of visibility. In the perceptual attack, we have the same objective, but now our constraint is that the phi of x minus phi of x prime in the L2 distance is less than rho. We do the same practice. We look at the first order approximation of the two. We have this convex optimization problem. We can solve it exactly. And now we have this term that depends on the Jacobian of the phi with respect to the input. This is the optimal direction that we should go. So what is the intuition here? Gradient tells me which direction I should go to maximally increase my loss. The other term tells me there are some directions that I can go further, but I don't change perceptibility of my image. So I can add larger magnitude noise without being perceptible. And this formula basically combines the two. So we want to increase the loss, but not being too perceptible. So when we apply this attack, the attack is basically really strong. In fact, if you have any defense, you should try against the perceptual attack, because to my knowledge, that's the strongest adversarial attack we have. You can see when this is the original image, this is the adversarially perturbed one. And here the lighting is changed slightly to create an adversarial example. Here the background is changed, the edges are changed, or the texture of this snowman is changed in order to create adversarial examples. And I want to emphasize, we haven't integrated these constraints in our optimization. These all come naturally because of the perceptual constraint that we have in our attack problem. Okay, so I started this part by claiming that we have a good approximation of the set of imperceptible adversarial example. But how can we verify that? So we do a mechanical torque study. So what we do is we show pairs of examples, clean and adversarial, to users and ask to see if they can notice the change or not. If the change is imperceptible, then probably they won't be able to tell the difference. If the change is perceptible, they can tell the difference. So with attacks generated by different threat models, we basically in the y-axis have the human perceptibility of the perturbations versus the x-axis, which is our neural perceptual distance. And you can see the correlation here. It is like amazing. It is above 85% correlation. Meaning that I could just look at the neural perceptual distance and tell if the users are going to be able to tell the difference between the x and x prime or not. In other words, in fact, this approximation is good, and we have a good correlation between the perceptibility and the neural perceptual distance. So we tried this on ImageNet, and for the sake of time, I'm not going to go into the details of this table. But here the rows are adversarial training based on different threat models like L infinity, L2, maybe all of them. And path means adversarial training against perceptual threat model that we introduce. Self here means we have the same perceptual and classification network. And AlexNet means we use AlexNet for the perceptual network. And as you can see, the numbers that we get for the union of the attacks or robustness against unseen attacks are significantly higher than the previous methods. This basically shows this method has a good generalization against unseen attacks. Okay, time to celebrate, this time probably for real. But there are several challenges remain. So far I have discussed robustness in the static setup. So you have an image classifier, it is static. What happens in adaptive learning, like reinforcement learning? So this is a much more difficult problem because An adversary can see the defense you applied in the previous times. Therefore, adversary can adapt its strategy. So we have a recent paper, it is going to appear in ICLR this year, that we have a provable defense against such cases. Let me finish this part. So you can also look at robustness in other complex prediction tasks, for example, in detection, that your output is not a single label, or robustness of beyond labels, like interpretation or fairness or other measures. Okay, so there was a question.
I mean, in the case of classifier and classifying an image if it is a torture or not, I understand the question. In reinforcement learning, what is the task that we're trying to protect?
So the task is the following. So you have an agent.
Okay.
An adversary, I can say, okay, adversary can perturb the observation of the agent within a L2 ball. Right? An adversary can basically use all of the perturbation in one time, or it can spread it over times.
Okay, okay.
And the goal is to make sure that the reward is bounded. So you have a defense that the adversary cannot lower the reward below a certain threshold.
And that actually you say that can be in every point, or it has some.
It is up to the adversary, and that is the adaptive nature of the attack.
Okay.
That makes the problem extremely difficult. So I'm happy to chat about it often. Okay, so that concludes the first part of the talk on adversarial robustness. Okay, so Costas, can we stay like maybe eight minutes that I can talk about the second part?
Let's say 5.
5?
Let's see how.
Okay, so the second part is basically we want to understand potential root cause of these issues. So we start with some thought experiments. For a subset of ImageNet samples, we collected segmentation masks for the entire object to test sensitivity of the models to backgrounds versus foregrounds. And we observe some really strange behaviors. For example, we take a robust ResNet 50 model. It has a very good clean accuracy. Now we add noise to the background in this case, and noise to the foreground in the other case. Right? So you expect that when you add noise to the main object, your model performance should drop quite significantly, and not so to the background. But we basically observe the opposite behavior. So when you noise out the main object, the probability of frog increases, versus when you noise out the background, the probability of the frog decreases, which should be the other way around. And it is not like a one-time thing. Even on other models, SimClear, we observe the same thing. And these are the pictures that I had in my opening slide. So you add noise to the deer, you expect the performance should drop, it increases. And you add noise to the background, and you expect the performance of the model shouldn't change, but it decreases quite significantly. So basically, we studied first the
Sorry.
Yes. Can you pause because
Yeah, let's take a question.
yeah offline I need to like go to some messages I have. So basically we studied robustness under foreground L infinity noise and under background L infinity noise in a plot like this. So y-axis shows general robustness. If your model is here, it means it is generally more robust. This axis shows model uses more foreground core features compared to background features. Okay, so we evaluated several models. Some of the messages that we have transformers, they have high general robustness. That is somehow expected. But we also have like some unexpected behaviors. This little red triangle is the robust ResNet. And this green one is the clean ResNet. And we see that robust ResNet actually has lower relative robustness compared to clean ResNet. It means that it uses background more than the foreground compared to the regular ResNet, which is somehow counterintuitive because you think about robustness, the robust model should somehow use more core and foreground features. This is exactly the opposite way. We have some hypotheses why this is the case, but this is an unintended consequence of adversarial training. And this is not just because of the hyperparameter. We tried different hyperparameters, even different resonant structures, the same thing happens. It is not a cherry-picked experiment. Okay, so I'll skip this slide for the sake of time. To study reliance of models on spurious features, we need large-scale data sets with rich feature annotations. But we have a lot of challenges here. The manual feature annotation is very expensive. You cannot go one by one and annotate your images. And you may actually miss some relevant features. And there are some spurious features that are not background. Look at this example. You have a class of desk, and there is a computer here. This computer is a spurious feature for this desk, but it is on the foreground, not the background. So it is hard to basically crop these types of images. And also we need to identify spurious features using general models. Can we do that? The answer is yes. So we have proposed a methodology that will appear in ICLR this year. So instead of annotating individual images, the idea is to annotate neural features directly using maybe a handful of examples. Let me be more concrete. We take a robust ResNet 50 model. We look at the penultimate layer neurons. For each neuron, I identify maybe 3-5 images that highly activate this neuron, 3 or 5. And I visualize this neuron for these images. And I show it to my AMT workers. And I ask them if this neuron that is visualized on these images, is it core or spurious? Does it highlight core parts of the image or spurious? That's it. So with 3 or 5 images, we annotate these neurons as core or spurious, and then I can automatically use these annotations to annotate the entire training and test set that I have in terms of their core and spurious features. So how do we visualize these neural features? We either use heat maps that highlight the important parts of the image. For example, here, this neuron highlights the mountain, but sometimes this can be a little bit tricky. Does it highlight the fence or the tiger here? It is not clear, right? Because we have an ambiguity here. In these cases, we use a method called feature attack that visually amplify these features on the image. So here, mountain has been amplified. So then it is clear the neuron is actually looking at the mountain. But here, fence has been amplified. Therefore, this neuron is actually looking at the fence, not the tiger. So it helps the users to do the annotation. So using this approach, now we present a data set called Salient ImageNet. So it has samples in this form. So it has X and Y like ImageNet, but it has 2 masks. One is the core mask, highlighting core parts of the image. And the other one is the spurious mask, highlighting spurious features in the image. And we provide this for almost the entire ImageNet dataset because of this scalable method that we have. More than 1 million samples, all classes. And this shows the number of images with at least 3 spurious features. And some classes like seatbelt, the top 5 features that we have, all of them are spurious. So these are extremely difficult classes. So using this, we can repeat the noise analysis. You can add noise to the core features and look at the model performance, that is the spurious accuracy. Because you're noising out the core features, you expect a high drop in the performance. Or you can add noise to the spurious features and look at the drop in the performance. And again, you expect a low drop in the performance. We look at, for example, a standard ResNet 50 model, a particular Drake class. Here we are adding noise to the core features. We expect a high drop in the performance. We get 0% drop. Here we are adding noise to the spurious part, which is the water. We expect a small drop in the performance. We get 41% drop in the performance. This is, for me, it was mind-blowing when I saw these results first. Basically, it should be the other way around. So I'll skip the rest. So we evaluated 42 models. We have basically shown some interesting behaviors. For example, there was a discussions on clip VITs that are very modern models. But if you look at their numbers, they basically mostly use the background information. So these are some of the analysis that can be very useful to go beyond accuracy. So we started with this data formulation that we have only label for X's, and the data comes from IID. And for that, we formulate the learning as an empirical risk minimization problem. But now we see that this doesn't work because the models, they mainly use spurious features. They are not robust. They are not interpretable. So my suggestion is to go back to the drawing board and rethink about data formulation. Maybe use richly annotated and diverse datasets like we have in the Salient ImageNet, that we have core and spurious mass, and that will potentially open up about thinking about new learning procedures for those datasets. So I'm not gonna talk about it. We have some recent attempt. We have a core risk minimization that we add noise to the input and we train a model that is insensitive to basically noise to non-core regions. And with that, we have really improved results, but it is still an open problem. And if you're thinking about some problems, that can be a good problem to work on. So let me wrap it up. So in the first part, I talked about adversarial robustness, provable robustness. We introduced a non-additive smoothing with splitting noise. In the second part of that, we talked about robustness generalization using neural perceptual threat models. And in the second part of the talk, we talked about reliance of the models on spurious features. We have two richly annotated datasets. Rival 10 is smaller, is manually annotated, and Salient ImageNet is basically automatically annotated, almost all of the ImageNet. So we are going to have some data releases of these datasets pretty soon. So if you're interested, please contact me. So I'll be happy to discuss some ideas we have. And that's it. So thank you, everyone.
Any questions? Thank you, Soheil. Any questions for Soheil?
Yes.
Thanks so much. Really interesting stuff. Could you talk a little bit more about like the where you're using like the Siamese networks to like do the perceptual networks, or sorry, to learn like perceptual like adversarial examples?
Yes.
You're not doing like a metric learning with the Siamese networks, right? Or could you talk a little bit more about that? I think I got lost a little bit.
Yeah, so basically in the perceptual one, so you use a perceptual network to extract these features, right? But who gives you this network? So one thing is that you can use a pre-trained network like AlexNet and use that as your feature extractor and use that as defining your threat model. That's easy. But you can say, okay, maybe I'm going to use my own classification network for the feature extraction. But if you do that, when you're doing adversarial training, your model changes. Therefore, your threat model changes. Right? So that's basically the second point that I mentioned. In fact, with the second one, we have an improved generalization number compared to the first one. Does that answer your question?
Yeah. So you're not like training the model specifically to like learn the perception.
No.
Like how to, okay, I see.
So I have a related question. So about the second part of your talk made the point that many of these networks at least look at the wrong places for labels.
Yes.
At the same time, I thought your perceptual distance kind of like relies on features extracted by something like AlexNet for what are imperceptible perturbations. So like, you know, like if AlexNet is picking the wrong features, why? I mean,
Yes.
Yeah.
Great point. So in the first part, we talk about very, very small changes. Like these are not like changes that basically have some meaningful natural changes in the image. So that's why AlexNet, the features that we extract, they seem to be meaningful in that regime. But in the second part, we are talking about some high-level features that can potentially be removed or be added compared to between the training and the test time. So these are like bigger changes that you have in your data. And you may say that, okay, so maybe this feature looks at the border, right? So this is like a bigger region. And it is okay because as humans, we also look at the context and we look at the background. But the issue is that when in the test time, you have a different object with the same context. Right? So these are bigger changes that you have. And in those cases, the model makes a mistake. Or maybe the more interesting example is this. You have a bird and there's a branch. A model looks at the branch to basically predict it's a bird. But in the test time, you have a branch, but then you have a frog on the branch. A model, because it looks at the branch, it says it's a bird. Right? So these are the basically larger changes that you have between your two distributions. In the first part, we are like looking at imperceptible changes, like very small adversarial changes that you have, and maybe because of that, the features are more meaningful. Yes.
So I have two questions. One, so how does this? Did you look at any of the results on the auto distribution? How would it change the performance of the models if you train with not a spurious feature? Basically, you don't learn the spurious features. And the second question is how much of this is translatable to NLP stuff? Because you mentioned that the transformers are actually really good.
That's fantastic. Two questions. Both of them are great. So in terms of like evaluating on OD distributions or distributions without like these spurious features, so we are starting to look into some of those problems, right? So we spend a lot of time in the second part just to get these annotations, not only useful for us, but hopefully useful for the community, right? To double check their high quality and stuff. But now we have those annotations and richly annotated data set. Can we think about learning, right? So far, we are just looking at accuracy measures like core and spurious. Or out of distributions, basically, we are noising out some of the core or spurious ones and see how model performs. And if we do some treatments like core risk minimization, we can see, okay, your clean accuracy roughly remains the same. Your core accuracy increases by 11%, but your spurious accuracy drops by 3%. So that is good. So the next step, we also want to look at the performance when you change your data set and you get like some natural variations in your spurious feature distributions or core feature distributions. We haven't done that yet. Hopefully, we think that with such approaches, you'll get a good generalization. And for the second question, I believe a very similar approach with the same framework can be used for NLP tasks. The idea, again, is not to annotate individual sentences or inputs, but annotate neural features. And maybe with some methods, like some models like, BERT or some other things, you can do that annotation and then highlight the parts of the sentence that are core or spurious for a particular prediction. When you have that annotation, then you can ask all of these questions and train better and hopefully improve models. Make sense?
So let's take further questions at the break. Thank you very much, Soheil.
Thanks, everyone.
And see you in 15 for Gutierrez talk.